making a representation, and maybe I hope that you will make a clear that basically will be actually in real life will be starting from DC, not from AC, right? So the AC really for the purpose of teaching. Go ahead.
Okay. Good afternoon, everybody. Thank you for coming out here today. My name is Steve Zudike, and I'm representing Team SIPA. As you can see, our title of our project is the high volt switch more power supply for three-phase AC aircraft. And in this project, I'll be talking about the motivation. Basically, this means what makes us choose this project and why we decided this is what we want to do. And after that, we'll talk about the project overview. Basically, this is everything about the project, the background, everything that makes up this project. After that, we'll step into the design constraint. Basically, this is all the challenges, difficulties, the sleepless night we have to deal with to get this work accomplished. And the approach, it means the steps we took in solving all these problems, how we implement the problem. After that, everybody want to see results, so we want to show the result. And this is our abstract. So I believe most of you here are into power or choosing or doing something similar to this. So if you're more interested in reading our abstract, our website is it's available 24/7. So feel free to go on there and take a look at the abstract. On our motivation, like I told you, there's so many projects out there, but we decided that this is what we want to do. Our main purpose of choosing this project because we want to design a circuit that consists of several IGBT transistors and use the PM pulse width modulation with a DSP so as to produce a system that can effectively produce 10 kilowatts of power with minimum power loss. Also, the pulse width modulation techniques generating a power supply could serve in the future. We believe it's going to serve as effective way of producing or converting power in the nearest future. Also, we aim to assist in improving power generation on unmanned aircraft. Also, we want to get more people to invest in this kind of method because they're good work for power generation and it doesn't cost that much. Also, our area of interest is to sponsor people that are going into electrical engineering worldwide, basically in third world and here in the United States. And this is our team. Right here we have Shola Olatijoye. He's right there. He's the group leader. He's done a good job. He's the circuit analysis, also the circuit design and the system engineer. Right there is me, circuit analysis and test engineer. And Philip right here, in the software program and the control analysis. Unfortunately, Agile, for some reason, he got into emergency this morning. He's not here, unfortunately. And he's the hardware programmer, circuit schematic, and webmaster. And right here we have our advisor at the top. He's been there. He's our primary resource, right from the one. Appreciate him being there for us and helping us out, telling us, directly leading us to the right path, and also that beeswax. And here we go. This is our technical constraint. This is all we have to deal with throughout the whole project. And thankfully, thank God, we accomplished all our technical constraints. Here we have our input voltage for between 110 to 120 volts, and the output voltage rectifier, which we use right here. Right here we have 172.5 for the rectifier that's converting the DC current to AC. So we have the output for the inverter we have 100 volt, and also the steady state frequency which we use right here is targeted 60 hertz, and also the maximum output power is 10 kilowatts. Then the test output voltage is 500 watts. Power supply to the gate drive between the range from 5 volt DC to 12 volts. Also the DSP control here will have a 1 kilohertz to 6 kilohertz carrier frequency. Our efficiency based on what we targeted from range from 85% to 95%. Also, this is our non-technical constraint. You can see here the cost, reliability, size, safety, input and output terminal. Based on everything we did, like I'm going to show you in the next slide, we're able to accomplish all this non-technical and the technical constraint. But we're still going to see that in the next slide. And this is our block diagram. Basically, this shows everything on the overall system. You can see right here we have our AC supply, which you use right here. This is rectifier that converts the AC into DC. Here we have the right here we convert from AC back to DC. Right here, you can see this is the load, and right here is the DC current supplying the voltage to the gate drive, and right here we have our DSP. That's a D-space that sends signal to the gate driver, basically. So this is basically the overall block diagram for the system. And also the same thing going on here, but this basically we use the MATLAB model to get this the system. Basically the same thing I just showed you now. And also this is also the system using the schematic design. This is also what we have right here, designing. But in this case, see the gate driver, the inverter, and the rectifier. This is the filter right here. So now we start out building. That was the whole idea. Here we have the three-phase rectifier. There we can see the whole system, the capacitor, like I told you, the filter, and the rectifier circuit. And this is our result when we test the output for the rectifier. This is what we have. The DC current, although this is supposed to be a straight line due to the noise and stuff in the system. That's why it wasn't really that great, but that's the result we have after that simulation. I do the output. And talking about the rectifier, as you can see, it's a three-phase rectifier circuit is used because it allows a less ripple, over a single phase. Also because it allows us to use a lesser value of capacitor to filter, like you can see on the system right here. We use only two capacitors, the big little thing that's what we're talking about. Then the two capacitors of the same value, we use the two capacitors of the same values to serve as the center tap. Based on I still gotta explain that in the next slide. Then so you can see the straight line there shows the DC current, like from the scope. The straight line right there represents the DC current going through. That's the output. Also now we have our inverter circuit. That's after converting the AC current to DC, we need the inverter circuit to convert it back to DC. That's what we build. You can see that's basically have our gate driver right here. But this basically the inverter circuit. We're going to show you the overall circuit and the result which we have after designing the whole system. And this is the D-space, which you use on displays and measure. And the D-space in this control the whole system basically. So you have the power to do whatever, change the frequency or the amount of power you want in the system. So D-space helps us to do that. And it generates the pulse width modulation signal to drive the gate driver and control the IGBT. The pulse width modulation compares the frequency signal, that's sinusoidal, and the carrier frequency triangle. I'm going to show that in the picture because it compares what it does basically. I'll show that in the next slide so you have better picture of what I'm talking about. Then also the output, it outputs the signal in the form of pulses with varying weight. So the weight of the square wave, as you can see, varies from time to time depending on the frequency. Also, the pulses would then be sent to the IGBT gate, which IGB will drop so it goes off and on, which is going to see in the next also in the next slide. This is the model from the MATLAB. This is the model we use. As you can see, this is the three-phase sine wave, and this is the ground. So basically, in here, there's inbuilt triangular wave. So basically, what it does when it sends the signal, automatically it's going to compare the both signal and then send the output to the gate. So that's basically what it does. So based on what result, this is the output from the pulse width modulation. This is what we got of the simulation. You can see this is your square wave we have. Also, now to build our gate driver. This is our gate driver with this. As you can see, this is the hose trap. This also would design this just in a way to prevent a short circuit, doing short circuit, and also reduce the chances of electric shock. So what you do right here, this is each of these gate right here controls each phase. So it's 3 phases of them. Each one of this one controls each phase of the power. And here is the gate driver, basically what I just explained. The gate driver helps convert the pulse width signal and pulse width signal produced from the DSP to a level where the IGBT gate can operate with. The circuit shows contain 3 IGBT gate driver operating 6 IGBTs of the 3 inverter circuit. Each of the gate drive circuit operates single phase of the branches. Basically, what I just said on the other slide. It also isolates the DSP from the power circuit. Basically, that's basically what it does. And this is the result, the output. Like I explained, you can see this is the high. They have the high side and the low side. So when it's high, basically what it means is on. When it's low right here, showing the white side means it's off. That's the gate driver. That's how it works. That's something I just explained. The gate driver allows pulses, and it's also shown by the gate switch on and off. That's basically when it's blue, that's when it's on. When it's off, it goes to the white side. So it's basically the high side and the low side. And the second, it allows the side. It allows the low side and the high side. So in this case, you have the chances of turning the switch off and on depending on what you want to do. That's basically the job of the gate driver. And the simulation shows just for the one phase. So basically, that the screenshot right there is just for the one phase of the gate driver. And this is the overall system. Right here, you can see our DSP. To measure this, the AC current, which we have here is 106 AC. And right here is the voltage going to the gate driver. That's the DC port going to the gate driver. And right here is the overall system. You can see right here we have the gate driver, we have our inverter circuit, and here we have everything all together. This is the rectifier circuit. So that's overall system. After we bring the whole system together and test it, we consider the output. And this is the output. Basically, this is just for 2 phase because the scope in the lab we cannot test for 3 phase, but when we test it for output for the 2 phase. This is the result. We have the sine wave. As you can see right here, shifted. You see the 120 shift by each other. So this is the simulation for the 2 phase. The 2 phase result. Because we cannot really test with this scope. We cannot test for 3 phase of the system. And then we did the calculation how we came about the for one level. So for the inverter circuit, we use 70 ohms resistor. Then the volt, which I showed you right there, is 106 volts. So to calculate the power, I have to time the volt, that's square. All over that will have this result right here, 481.5 watts. Then the power in the rectifier circuit, that's what we did basically. Power is the current and volt. The volt is 172, and the current drawn from the circuit from the rectifier system is 2.94. So the total power right here is 505.68. Then efficiency, how we test for efficiency right here, like use the output power over the input power times 100. That's what we did. This right here, divided by this, we have 95% efficiency. Then accomplish basically for the overall, basically this all we got accomplished for the prototype 2. The rectifier circuit, the LC filter circuit, the D-space with a pulse width modulation signal, the gate driver, and the inverter circuit. And this is our cost. Based on all the materials we use and everything, this is the cost right here come up to $199, so approximately $200. But this sounds so real, I mean, too good to be real, because Dr. Visuals provided us with the DSP, which was supposed to cost us at least $6,000 or $5,000. So that's why you're looking at this. But don't get deceived over there. So we thank you for being, providing us with that. So that's how we end up with the $200. And this is our PCB design using the ebook. So this is basically the same system I showed you, the overall system. Everything is right here. It's the inverter circuit, the rectifier, the inverter, the gate, and the DSP. So using ebook, that's how we came up with the overall system. I guess
Any questions? We have time for two. You are not allowed right now. Yes, oh, you don't have?
I have a question. What happens if you put an input which requires more power than the system? What happens? Do you have a fault protection circuit that disables the system from collapsing, or what happens in that situation?
That's what, like you can see where I said the bootstrap. So in case of situation like they'll have that, that's why we use the system bootstrap. But in this case, we can't really put, that's why we have a specification. You can't really go above the requirement, but in that case, the bootstrap, that's the gate valve is going to shut down because you have the bootstrap to protect against short circuit or anything. So,
like, what do you mean, like 110 volt?
Yeah.
More than 120?
More than 100 feet.
Okay.
but what we're designing basically is not going to handle anything above there. Our specification is for 110 volts. That's the specifications. Anything above that is
There
going
could be
to.
glitches in the system and it sends more than 110 volts. So
Yeah, it could be able anything above there, but it's not going to be exceedingly like too high. But anything 120, 130, it could be able to handle it.
Any other questions? Okay, go ahead.
For the DSP, do you write the code or?
Yeah, DSP will use the C++ code with the flow. Yeah, we use the C++ to program the DSP.
Okay, I have a,
I have a question.
who is there?
Go back to the waveform, please. Go back to the.
Which of them?
Go back. Yeah, that's yeah, this one.
Okay.
From you're talking. I'm asking this question because it's interesting. And you told me this is wrong. From your.
I don't know about your project.
No. From your question. Is there any phase shift?
Make it brief because we don't have
Is
time.
it any phase shift among the
If the up and down is a shift 120 degrees apart from each other, I mean, it's 120 degree shift, right? One is going up and one is going down, so it's the shift.
Okay, let me, okay. I think what you have in here is that the second phase should really have the same magnitude as the first phase, which is not. And also the 120 degree phase shift is not there. So what you really should do right now is this is the first phase alone, standalone, second phase standalone, make sure why the second phase is not really going all the way up.
Yeah, I guess we did the same thing, I guess, from the scope. We did the first, the scope, we tried the first one, that's the first phase, try the second one. So when you add the both together, that's how it came up. But testing it separately, like individually, we have the same, not the right result.
So something is funny because your input, the very first input,
Right.
is 3 phases and all of them are 120, right?
Right.
So your output should be the same. But right now you have one high and one low, so there must be something either in the PWM which doesn't give you the high, So try to fix the PWM for the second phase because maybe it is not correctly shifted. Or if you like, you make single phase, each one single phase, and then superimpose both of them and see exactly what happens. Like store the first one, store the second one, and see if there is actually 120 degree phase shift and same magnitude.
Right.
So if everything is okay, then something wrong with the circuit when you connect it together.
Okay.
And maybe you should remove the load, just take the load out because maybe the load has some variation which causes the voltage to drop. Just test it as an open circuit.
Okay.
Anyway, thanks very much.